Sorry. Okay. Yeah, so we can distribute that sort of intelligence or control to loads. So the autonomous control, which I sort of came up with there, spent some time sort of trying to come up with an acronym for it, being autonomous control of electric devices, which actually makes a word aced. However, other people throughout the world have sort of had the same ideas. I'm not alone. So it might be self-organizing power systems, or autonomic power systems, or autonomous energy systems, organic distribution systems, or grid-aware flexibility. So there's all sorts of names. The idea is really the same. Measure the power quality at the point of your load, generally the voltage, could also be harmonics. Filter those time series so that your load isn't actually interrupting your learning process. Interpret a probability distribution function in its very simplest form. Calibrate a response or a control response. And then in real time, you go through and you're measuring the power quality, and then you're enforcing those control actions depending on what that voltage state might be and what your load is wanting to do. So for the EEA conference in August, I won't go through this, but I presented simulation results using OpenDSS, which is a small piece of software that simulates loads in a distribution network. Assume that we got 30% electric vehicles in this network, use some data behind it, some data sets based in the UK, and then looked at whether or not this idea of autonomous control can break up a load spike caused by all of these EV chargers turning on at 6 o'clock in the morning. So you sort of, this is the process, you measure your voltage. I've got a probability delay function. So the EV charges can be delayed depending on what the voltage is relative to what it would normally be. Of course, once you get all these EV chargers trying to switch on, some of them do, the voltage decreases, and then the other EV chargers which haven't quite got there, they get delayed until the voltage recovers because some of those EV chargers will have stopped. So you can break up this load spike. And shown here, the results at the top there, the total circuit load without sort of some control or load smoothing. You end up with this great big spike with that red line. And then the magenta line shows that you can break up that spike and spread out that load a little bit. But I also noticed, having done this, that, wait a minute, the same thing is actually improving in the for the normal conditions of network load. So the dark blue line there is the sort of normal network load where I haven't got all those EV chargers starting at the same time. They're just starting throughout the day, depending on when the data set sort of probability said they should start. Whereas the cyan line there is when that autonomous control is given to those EV chargers and they start reducing that load peak. So it should be possible to actually apply this same theory, obviously, to other loads like hot water and or EV storage or any other device that's got a little bit of control intelligence around it. So I thought, well, in my house, I have a particular problem. I have just got solar panels and I've got a hot water heater, but I've got my meter in the garage, I've got my solar panels on my carport, and I've got my hot water cylinder in my house, and I've got corrugated iron walls between it all, so I've got no Wi-Fi signal, so I can't just go to the shelf and buy a hot water diverter and install one of those. So I thought, well, I shouldn't need to have something communicating between the meter board and my hot water cylinder. I should be able to just look at what the voltage is and do this. So I got some data from my meter, and you can see at the top here, before I had solar panels, my power was black. Then I got solar and it turned blue, which is better. It should really be green, shouldn't it? And then separate out the voltage during the day, the voltage profile for times when my power is exporting, i.e. my solar panels are generating more than I'm using, and times when I'm importing, so importing the lower graph, the blue, upper and lower quartiles there, and I can find this relationship, which is nice to always have an equation, which shows that basically for 75% of the time, the voltage when I'm exporting is greater than what it would be otherwise if I was importing, i.e. you can work out when
my solar panels are exporting, therefore I should be able to build a hot water diverter. I haven't done this because I'm lazy and haven't got there yet, but the potential of this is to help with hot water heating. So that problem of ripple controllers all going out are being replaced by flexibility devices. Maybe this is a way to actually give something back to the consumer where they are going, no, we don't have to cede all of the control for our load to the flexibility provider, but we can be rewarded for doing it ourselves without thinking. Heat pumps and refrigeration, other smart loads. Irrigation loads. I had a problem when I was working as a power quality engineer up in the Ida Valley. You've got all these irrigation pumps. They all turn on at the same time. The network voltage collapses and the farmers ring up the power company and they go, oh, why is this happening? And I'm sitting there and go talk to your neighbor. Well, they shouldn't really need to because they should be able to work this out. And then also when you've got things like the Iberian blackout and you've got the voltage going all over the place. Well, if you've got devices which are responding to in accordance to what their normal range of voltages are, of course, once the voltages start going out of range, they're going to start doing smart things to bring that back into range. And it's dependent on using it as a learning algorithm. It's independent of where you are in the network. So it's got to be independent of whether or not you're close to the transformer. So the quantity of voltage drops relative to what your normal range is. And then local network trading. The problems, of course, are the DNO doesn't just sit there and do nothing. They're changing taps, they're changing switching, and there's, of course, other load interactions going on. So and acceptance and understanding. Some loads are sacrosanct. You can't touch a kettle during halftime in the football, so you don't want to delay that. Other loads, consumers really not aware of what's going on with them. Remuneration, there's no sort of economic model to incentivize consumers to do this, which is another problem with the flexibility and why ripple control is hard to maintain because there's those remuneration problems. And then actually measuring what is the benefit to the network operator from doing these load control type measures, and how can they work out what that true benefit is. So yeah, in summary, you can have market signals or power system problems that lead to diversity collapsing and load spikes. Loads are unresponsive to power quality by and large, whereas autonomous controllers that learn a normal system state can respond accordingly, and you can do things, like reduce the load spike, and the potential is quite wide for this, but surprisingly, such a simple idea hasn't really been researched or discovered very much. So hopefully we'll be able to progress some of that.